Okay, so I picked an example out of WebWork here. Homework 4 problem 3 is going to be the one that has the repeated roots. And it's the same question as the previous ones, basically just with a different differential equation. Find this general solution of this differential equation, but this time, as you might guess from 14 being 2 times 7 and 49 being 7 squared, this is one that has repeated roots. Okay, so here's the differential equation, and as usual, we guess x equals e to the lambda t, and we get a characteristic polynomial. When we plug in our guess and cancel out the e to the lambda t, we get lambda squared plus 14 lambda plus 7 equals 0. But look, this is a square. So this is lambda plus, no, it's not a square because I made a typo. This was 49. So this is 49. And now it's a square. Lambda plus 7 squared equals 0. So we got the root lambda equals minus 7, and we got the other root lambda equals minus 7, but it's not really another root. So this is the repeated roots case. And so the solution, well, one solution is x1 of t equals e to the minus 7t. But problem, we need another solution. So what do we do? And then the answer, discussed last time, the answer is multiply your first solution by t. And I'm giving you no motivation for why that's what you should do. All I gave you is this unsatisfying argument that it works. Look, it works. So that's just what we're doing. Okay, so this will work. And if you really want to try it and see that it works, you can substitute it in. But why would you do that? I'm telling you it works, right? And we just made a general argument and saw why it works in general. Okay, so then what's the general solution? Is C1 times this, C1 e to the minus 7t plus C2 times t e to the minus 7t. That will be the general solution. So that should work. And yeah, the rest of this problem is basically the same kind of stuff, solving different initial value problems. The same principle that we discussed last time that helps you solve this part more easily using the first two parts. That same principle applies. We're still looking at a linear differential equation. One thing to watch out for when you're doing these two parts, when you're solving initial value problems, is when you're imposing these initial conditions, you're going to need to compute the derivative, right? Like you need to compute x prime of t and then plug in 0 and then set it equal to 0 or 1, depending on which one you're doing here. Watch out for the product rule that's going to show up. If this is your x of t here, then when you compute the derivative of this will be negative 7c1 e to the negative 7t. The derivative of this will require a product rule because it's a function of t times another function of t. So I think if I don't make a comment about that, a lot of people will probably forget about it.